Jai Hind students, welcome to my YouTube channel. Students, I will start this session with the saying that the present and the future success depends entirely on our action. That is, it depends entirely on ourselves. Let us never look outside ourselves for help. Actually, students, no one is going to help you except yourself. All the success or failure entirely depends on our own actions, on our own decisions which we make. Right, students? So, be responsible and be prepared to make those important decisions which will make you succeed in future. Right, students? Well, with that, let's begin this session. Today we are going to discuss the expression for the magnetic force experienced by a current carrying conductor under the influence of magnetic field. Right? So, we need to find out the expression for the magnetic force. So, what to do is, we'll consider a current carrying conductor. It is lying horizontally, say along x-axis. Suppose this is the origin and this is the x-axis. So this is a conductor, say of cross-section area A. This is the cross-section area A and length, suppose L. And let's also consider N be the total number of electrons inside the conductor. Electrons are the charge carriers, right? And small n be the number density of the electrons. Number density of electrons means total number of electrons present in the conductor per unit its volume. Right? So, this is the number density of electrons. Number density of electrons. That is the number of electrons which are present inside the conductor per unit its volume. And this conductor, obviously being in the cylindrical shape, its volume would be cross-sectional area multiplied by length. So what we get is number density of electrons would be total number of electrons divided by volume. Volume is cross-sectional area multiplied by length. And remember students, N, capital N, it's the total number of electrons. It obviously will not have any unit. While small n is the number of electrons per unit volume. So the SI unit of number density of electrons must be per meter cube. So in terms of number density of electrons, the total number of electrons present inside the conductor may be written as NaL. Put this as equation 1. Small n, it's the number density of electrons. Capital letter A, that's the cross-section area of the conductor under consideration. L is the length of the conductor, right? Let us assume the current to be flowing along the x direction. This is the direction along which the current is flowing. Now we are aware, students, this is the direction of the conventional current. Electrons being negatively charged particles or carriers, it will drift in a direction opposite to that of the conventional current, isn't it? So electrons will drift along this direction towards the negative x-axis, like this. These are the free electrons which will drift in the opposite direction. And we must remember the electrons inside a conductor drift under the influence of electric field with drift velocity Vd. So Vd, small letter v and d, it stands for the drift velocity. It's always in a direction opposite to that of the flow of the conventional current, right? So this is a current carrying conductor, and suppose this current carrying conductor is under the influence of a magnetic field. Let us assume it to be directed along y-axis. OY is along the positive y-axis, right? So what we have assumed is, we have assumed a current carrying conductor to be lying along the OX, that is x-axis, and it is under the influence of magnetic field directed along y-axis. Clear? So our objective is to find an expression for the magnetic force experienced by this current carrying conductor under the influence of this magnetic field, right? So what we do is, students, in the unit of current electricity, we are already aware of the relationship between the current flowing through a conductor and the drift velocity of the electrons, right? So, current I and drift velocity Vd are related by I is equal to NEA Vd. Vd is the drift velocity. Now, current is a scalar quantity, we are aware of it, right? But current element, it is treated as a vector quantity. Current element is current multiplied by length of the conductor, and that should be taken along the direction of the flow of current. So that IL will become current element. So what to do is, let's multiply both the sides by L. So what we get is NEA Vd multiplied by L. Now this is vector and this is Vd is also vector. So in the vector form, we can write it like this. This is in magnitude, right? So in the vector form, this becomes current element, current multiplied by length. So that is the current element, always measured along the direction of the flow of current. So current element, magnetic field at a point is due to current element, which is a vector quantity. SI unit obviously would be ampere meter. So left hand side, if it is written in the vector form, then we need to write the right hand side also in the vector form. Here, number density of electrons, charge, area, length, these all are scalar, but velocity is vector. So what to do is, it will be minus NEAL Vd. Students, why this negative sign? Because charge, electrons, it is negatively charged and it drifts in a direction opposite to that of the direction of the current element. Look at this particular diagram. The current element, it will be, if the length of the conductor is measured along the positive x direction, so the current element IL vector will be along x direction, right? Electrons, it will drift in the opposite direction. So Vd and IL both are oppositely directed. So that is why this negative sign is to be assigned over here. So put this as equation number 2. So these are the two facts which we'll be using, right? First is the total number of electrons inside the conductor in terms of the number density of electrons will be given by capital N is equal to small n AL. Second is, we are already aware of the relationship between the current and the drift velocity. It is I equals to NEA Vd. Multiply both the sides by L and then write it in the vector form. IL is treated as current element, right? So in the vector form, this will be the result. Now students, as per magnetic Lorentz force, we are aware the magnetic force experienced by a moving charge under the influence of magnetic field, that is given by, in the vector form, it is given by F vector equals to Q V vector cross B vector. This we are aware. Here, using this formula, the magnetic force experienced by an electron inside the conductor, that will be given by F is equal to electron, it's negatively charged, so Q will be replaced by minus E, right? V, the velocity with which the electron drifts, is represented by Vd vector cross B vector. This is, students, as per the magnetic Lorentz force. A single electron, that is a single electron inside this current carrying conductor under the influence of this magnetic field will experience this force. So what about the total force experienced by the conductor, which contains n electrons? It will be equal to n times the magnetic force experienced by a single electron, isn't it? So therefore, net force experienced by the conductor, by the current carrying conductor, which contains n electrons, it will be definitely given by F vector is equal to capital N times small f vector. I hope you have understood this concept. Students, this is the magnetic force experienced by a single electron, and this conductor contains n electrons, capital N electrons. So total force experienced, total magnetic force experienced by this current carrying conductor containing n electrons would be obviously given by capital N times the force experienced by a single electron, isn't it? So let's substitute the value over here. What do we get? Capital N, it's equal to small n a l. What about f vector? It is minus e vd vector cross b vector, right? So let's rearrange the terms. What we get is, it can be written as minus n a l e vd vector cross b vector. These all are scalars, only the drift velocity and the magnetic field. These are the only two vectors. And the cross product or the vector product can be only between the two vectors. These are scalars. Now students, make use of this equation 2. Minus NELVD minus NEALVD. It can be written as minus NALEVD. It can be written as IL vector, isn't it? Therefore students, F vector is equal to IL vector cross B vector. So this is the formula, or rather the expression for the magnetic force experienced by a current carrying conductor under the influence of magnetic field. Here IL vector is equal to, from equation 2 actually, it is equal to minus NALEVD. Right? That is from equation 2. So this is the expression. So net force, net magnetic force experienced by a current carrying conductor under the influence of magnetic field is IL vector cross B vector. IL is the current element, B vector is the magnetic field. And remember, this is the cross product. A cross B is equal to AB sin theta n cap, isn't it? So F vector must be perpendicular to both IL vector as well as B vector. So now let's discuss its special cases. Now students, what we do is, using the properties of the vector product, we can safely conclude that the direction of the magnetic force is both perpendicular to the current element as well as it is perpendicular to the magnetic field, right? So what we have obtained is magnetic force, it is equal to IL vector cross B vector. F vector is equal to IL vector cross B vector, right? So by using the properties of the vector product, we can safely conclude that F vector is perpendicular to IL vector and F vector is perpendicular to B vector. That is, students, the magnetic force, it must be perpendicular to both the current element as well as the magnetic field. It should be lying perpendicular to the plane containing IL vector and B vector. Is it clear? So let's consider the special cases, and then in the later section we will discuss the rule so as to determine the direction of the magnetic force experienced by a current carrying conductor under the influence of magnetic field, and that is actually known as Fleming's left hand rule. That we will discuss after we concentrate on the special cases, right? Let's consider on the special cases. Okay, case 1. Case 1 is when theta is equal to 0. Now look students, if you expand it, what we will get is IL B in magnitude. It will be equal to IL B sin theta. Theta is the angle between the current element and the magnetic field. A cross B is AB sin theta, isn't it? Theta is the angle between A vector and B vector. Over here it is IL vector and B vector, right? So if theta is 0, what will be the diagram like? It will be like this. This is a current carrying conductor. Current is flowing along this direction. So current element would be along this direction, and magnetic field is also along this direction. So here we are aware sine 0 is 0. So therefore magnetic force over here, it will be equal to ILB sine 0. So sine 0 is 0, therefore it will be 0. So students, whenever the conductor, current carrying conductor is placed along the direction of the magnetic field, then the conductor won't experience any magnetic force, right? Similarly, when theta is 180 degree, that is, this is the current carrying conductor, and suppose the current is flowing along this direction and it is placed under the influence of magnetic field, which is in the opposite direction. So what's the angle between current element and magnetic field? As per the diagram, it's 180 degree. Now sine 180 degree is also 0. Therefore, here also the magnetic force, it will be equal to ILB sine 180, that is 0. So that magnetic force will also be 0. So students, from case 1 and 2, what we conclude is, if the current carrying conductor is placed along the direction of the magnetic field or opposite of the direction of the magnetic field, in both the cases, it won't experience any magnetic force. Clear? Third case, case 3. This is the diagram. This is the current element and this is the magnetic field. So what's the angle between these two? 90 degree. Right? So case 3 is when theta is equal to 90 degree. Sin 90 we all are aware its maximum, it is plus 1, isn't it? So here F would be equal to maximum and it is equal to BIL sin 90, pi by 2. Sin 90 is 1. Therefore, maximum magnetic force which a current carrying conductor can experience under the influence of magnetic field is BIL. This is the formula. Please do remember it. Right? So, I will recap the cases. If the current carrying conductor is placed along or opposite to the direction of the magnetic field, then it won't experience any magnetic force. A current carrying conductor experiences maximum magnetic force when it is placed perpendicular to the direction of the magnetic field. And the expression for the maximum magnetic force is BIL. You can remember it by remembering BIL, BIL, right? B, magnetic field, IL, it stands for the current element. So this is the expression for the maximum magnetic force which a current carrying conductor under the influence of magnetic field can experience. Now students, this was regarding the magnitude. Now regarding its direction, and that is given by Fleming's left hand rule. So students, Fleming's left hand rule. This is a rule which is used to determine the direction of the magnetic force experienced by a current carrying conductor under the influence of magnetic field. And this rule is applicable only when the direction between the current element and the magnetic field is 90 degree. Remember students, we are aware F vector is equal to IL vector cross B vector, isn't it? So in case of any angle between them, the direction of F vector can be easily calculated by using the properties of the vector product, isn't it? We know how to find the resultant R vector if it is given by A cross B, right? In that case, we make use of thumb rule, isn't it? The angle IL cross B, the angle is to be measured from IL to B. So the fingers must curl along the direction of orientation of the angle. Then the thumb will represent the direction of the resultant of the vector product of the two given vectors. So that is one method, right? And this method is applicable whatever be the angle between these two. But this rule can be directly applied when the current element and the magnetic field are perpendicular to each other. Only in that case this rule is used. So please do remember, there shouldn't be any sort of confusion, right? So students, Fleming's left hand rule is used to determine the direction of the magnetic force, which is experienced by a current carrying conductor under the influence of magnetic field. And this rule is applicable only when the angle between the current element and the magnetic field is 90 degree, right? So, as the name suggests, left hand rule. So we have to make use of left hand, isn't it? So what we do is, this is my left hand, right? You need to stretch the thumb, the forefinger and the central finger of your left hand such that they are mutually perpendicular to each other, right? Again I repeat, stretch the thumb, the forefinger and the central finger of your left hand such that they are mutually perpendicular to each other. All are perpendicular to each other. In that case, if the central finger represents the direction of the flow of current, the forefinger represents the direction of the magnetic field, then the thumb will represent the direction of the magnetic force. Clear? If you apply this rule over here, look, this is force, this is magnetic field and this is current, right? So if you apply this rule over here, this is magnetic field, this forefinger, so it will be like this. This is current along the x-axis, so current is represented by the central finger, so it is like this. So this indicates, central finger indicates the direction of the flow of current through the conductor. The forefinger of the left hand represents the direction of the magnetic field. Then the thumb will represent the direction of the magnetic force, which in this case is in the outward direction, that is along z-axis. So the magnetic force in this case would be along this direction. Suppose it is z-axis. So the magnetic force would be along this direction. This is the direction of the magnetic force, which is along the positive z-axis, right? So let's discuss the rule again. Suppose this is the left hand. This is suppose the left hand. Right? This is, all these must be mutually perpendicular to each other. All the three must be perpendicular to each other, right? This is the thumb. Suppose this is the thumb of the left hand. This is the forefinger of the left hand. And let us consider this to be central finger of the left hand. Right? Like this. This is the left hand. So this is the thumb, this is the forefinger and this is the central finger. We need to stretch the thumb, forefinger and the central finger in such a manner that all the three are mutually perpendicular to each other. Right? In that case, you can remember, students, you're aware of FBI, isn't it? FBI. It's a commonly used term. It's a secret agency in US, United States. The full form of FBI is Federal Bureau of Investigation. So just remember by that. This is F, force, this is B, magnetic field, and this is current. So students, simply remember FBI, Federal Bureau of Investigation. Right? So, again let me repeat this rule. If you stretch the thumb, forefinger and central finger of your left hand such that they are mutually perpendicular to each other, then if the central finger represents the current, the forefinger represents the magnetic field, then the thumb will represent the direction of the magnetic force. So students, this is F, thumb is F, forefinger is B, which is magnetic field, and central finger represents the direction of I, which is current. So FBI, just remember this in sequence, right? I hope you will obviously remember it. And this rule is applicable so as to find out the direction of magnetic force experienced by a current carrying conductor under the influence of magnetic field, right? And this rule is applicable only when the angle between the two is 90 degree. Then only this rule is applicable. Clear? So let's apply this rule in some situations, right? So let us practice this rule. What we do is, we'll consider, suppose a current carrying conductor is placed horizontally such that the current flows from west to east, right? So let me represent it diagrammatically, right? This is the current carrying conductor. This is suppose the current carrying conductor, and let us consider this to be west and this is east, and let us consider this to be north and this is south. Obviously all are perpendicular to each other, no doubt regarding this, and this will be the vertical. This will be the vertical. Okay. North, south, west, east, all are in the horizontal plane, isn't it? Now let us assume this current carrying conductor to be lying in the west-east direction such that the current flows from west to east. Let us consider the current to be flowing from west to east, and let this conductor be under the influence of magnetic field, perpendicular magnetic field directed from south to north. So magnetic field is directed from south to north like this. Like this. This is the direction of the magnetic field. Let us consider this to be the direction of the magnetic field. That is from south to north. And what's the angle between these two? 90 degree, obviously, right? So if this is west, this is east, that will be north and this will be south, right? So current is flowing from west to east and the magnetic field is from south to north along this direction. So if you are asked to determine the direction of the magnetic force experienced by this current carrying conductor, then what will you do? We'll make use of Fleming's left hand rule, right? Let's try to apply this rule. This is F, this is B, this is I. Remember students, Federal Bureau of Investigation, FBI. F stands for force, B stands for magnetic field, I stands for current. So let's apply this. This is current, central finger, that is from west to east. This is magnetic field, right? Magnetic field, that is from south to north. So thumb is indicating in the upward direction. So applying this rule, we can safely conclude that in this case, the conductor will experience a force in the vertically upward direction. This is the direction of the magnetic force. Again, it will be perpendicular to both the current element as well as the magnetic field. All the three are mutually perpendicular to each other. Clear? I hope you have understood this rule, and we have also discussed all the three special cases. Isn't it? So there are various applications of this expression for the magnetic force. F vector is equal to IL vector cross B vector. And we will be making use of this Fleming's left hand rule very often, very frequently. So students, please do practice this rule in solving certain numericals in respect to finding the direction of magnetic force, right? So we will continue in detail some applications of this in the next session. So for this session, that's it. So do join me in my next lecture then. Thank you.